And here. Okay. Something you can take notes with, something you can take notes on. Susanna, you're leaving early?
Yeah.
Okay, go when you need to go, but leave like 3 minutes before you thought you needed to go and swing by Mr. Grosbeck's office. He came up to find you during the assembly and you were obviously gone. He just asked if you'd stop by. Okay. So guys, beginning of chapter 4. I understand there's some competition here in the school. I've been claiming for about 1.5 years now I have the best pencil sharpener in the school. Oh, no. No. Oh, yeah. No, so not Peck. Beard. Rice. I hear there's rumor he may have a good one too. Apparently his has like a little light that comes on when the pencil's sharp. We may have to have a sharpen off at some time during lunch. We'll see. Okay, so guys, join me if you will on page 115. No, guys, you got to get this. Do it now, but don't ever do this again. We're going to get to work. Not bad, right? Yeah, see? Careful, you could hurt yourself with that. All right, so guys, all I want to do with you right now, because remember last time in class we shot through chapter 3 like that's how we roll? That's not how we roll. I want you to join me at the beginning of chapter 4, because I just want to read the title with you. This is, in the words of our good friend Mr. Ellingford, important. You know how he overpronounces everything? Yeah, including his own name. Okay, so, guys, this is very important. Read the title. What does it mean? What does aqueous mean? In water. So guys, you'll notice that it's the title. And because you understand that all of these chapters are set up like outlines, the title becomes the all-encompassing idea that will then blanket the entire chapter. And guys, it's critical that you understand this in order to move forward. Aqueous means in water. So what is going to be literally the context for everything we're going to talk about for the rest of this unit? It's all in water, okay? So you need to be you need to be thinking this is happening in water because the title of the chapter tells you this is all aqueous chemistry. So guys, let me set the stage for you. What you're going to find out over the coming days is that generally, there are 3 types of water-based chemistry that you need to understand in this class. One of them is what is called precipitation chemistry. We're going to do that today. We'll do a lab in the coming days. Then, guys, the next one is acid-base chemistry. We are going to touch on that in one class period, just so we know enough that we can talk about it generally for the remainder of the year. But, guys, in February, we're going to spend 5 weeks on acid-base chemistry. So you're going to get a little taste of it today, and then we're really going to get into it in February. Then, guys, the third type of aqueous chemistry that you're going to learn in this unit is oxidation reduction chemistry. Again, I'm going to give you a little flavor of it today, and then that will be the last unit that we do, chapter 20. That'll be in early March, and that'll be the last thing we do. Is that you clicking, Tony? Stop it. Okay, so guys, again, the idea here is we've got 3 types of aqueous chemistry to talk about, but we're going to just touch on them now and then we're going to dig deeper later. Do you get the idea? Okay, so today, guys, what we're going to do is this. In order to talk about, did none of those scores record?
I think so. Just frozen.
Oh, yes, you're right. That is frozen. Sorry. Thank you. So, guys, in order then to talk about aqueous chemistry, guys, what we're going to do today, here's our outline for today. We're going to start by reminding ourselves what happens when things dissolve in water. As we talk about that, we're going to talk about some new terminology. Then once we've talked about how things dissolve in water and how we talk about that, we're then going to focus our attention on precipitation reactions. So that's why you summarize the solubility table, because in order to understand precipitation, you've got to understand solubility. So Samuel, that's where we'll bring that back. I didn't want to collect your summaries of that solubility table because you're going to use them starting right now. So guys, do you get the idea? Are we okay? All right, so here we go. So guys, in order for us again to talk about things in water, we need to talk about solutions. So guys, this is stuff you want to get in your notes. So guys, when we talk about solutions, and this part isn't in your notes, but I think you remember, guys, solutions have two parts, right? When you put salt in water, the salt dissolves in the water. What do we call the water? The solvent. What do we call the salt? The solute. So guys, I didn't even include those terms because I figured that you were familiar with them. If you want to write them down, you can. So the solute is the thing being dissolved, and the solvent is the thing doing the dissolving. Now guys, when things dissolve in water, this can happen in one of two ways. You learned this last year. We're going to dig into it more today. Guys, sometimes when things dissolve in water, they form what are called non-electrolytic solutions. So some things, when they dissolve in water, they don't function as electrolytes. What that simply means is when they dissolve in water, they don't conduct electricity. Now guys, you understand this, right? Water does not conduct electricity. Did you guys know that? So when you're in the Sierra Park pool and a thunderstorm comes in and they kick you out of the pool, they obviously don't want you to get electrocuted, right? But guys, understand there's no safer place to be than swimming in a pool full of water. A pool full of water could get hit by lightning and you would be okay. Water does not conduct electricity. So what's the deal? It's the stuff dissolved in it, the chlorine and other things. So guys, water itself does not conduct electricity. It's the stuff that's dissolved in it. So when we dissolve stuff in water, some things when they dissolve don't conduct electricity. So what's true of those things? Well, first of all, they do dissolve. Guys, don't confuse this with not dissolving. So they do dissolve. What they don't do is ionize. So non-electrolytic solutes do dissolve. What they don't do is form ions. Because they don't form ions, they don't conduct electricity. And guys, an example of this would simply be sugar. Does sugar dissolve in water? Yes, it does. But guys, sugar does not break into ions. And I'll show you representations of this in a minute. But guys, sugar does not ionize when it goes into water. So in theory, you could be swimming around in a pool full of sugar water and you wouldn't get electrocuted in a lightning storm. Yeah. They do. They break into molecules, and that's the difference. So a non-electrolyte is a substance that doesn't break into ions. So why doesn't it break into ions? Because it's covalently bonded. So covalently bonded solutes, when they dissolve, and I'll show you videos in a second, the molecules stay intact. So if you throw sugar into water, it does dissolve, but the things that are being carried away by the water molecules are sugar molecules, not the things that make up the sugars, but the sugars themselves. And those sugar molecules are not charged, and therefore they don't conduct electricity. Do you guys understand that? In order to conduct electricity, you need charged particles. Electricity is a charge, so to conduct a charge, you need a charge, and if this thing that dissolves isn't charged, it doesn't conduct. Okay, so when you think non-electrolytes, think sugar. So what about electrolytes? Well, guys, electrolytes do conduct electricity. So again, these solutes are soluble. but when they dissolve, they do break into ions, and as a result, they conduct electricity. Examples of that are things like table salt. When table salt goes into water, it not only dissolves, it ionizes, and because it ionizes, it can conduct electricity. So guys, I know the words maybe are helpful, but I think you'll really understand this when you see the animations. Guys, understand these are animations, they're not simulations. This is more like a cartoon than a computer-generated representation of what's actually going on, but I think it'll help you visualize it. So what I'm going to do is I'm going to show you an animation first of salt dissolving in water and then sugar dissolving in water, and I think you'll see the differences. You ready to go? Okay, so it goes like this. So down here in this Florence flask, we have water, and what we're going to do is we're going to dump in a cube of salt. Not sugar, it's salt. And when the salt goes in, we'll then zoom into it. And it looks actually like our model for salt, right? Only it's two-dimensional. But then, guys, what happens is these water molecules come in like little tugboats, and intermolecular forces form between the ions and the water molecules, and these intermolecular forces allow the water molecules to surround the ions, and these ions get pulled off into solution. Now, guys, the presence of these ions now allow the salt solution to conduct electricity. So these water molecules come along, intermolecular forces create attraction. The attraction rips the salt crystal apart. These ions go off into solution. And then, guys, if we were to take this solution and if we were to hook a circuit up to it, and pass a current through it, so a positive and negative pole, and pass a current through it, the light bulb would light up because it will conduct electricity because of the presence of those ions. Does that make sense? Okay, so now let's repeat this with sugar. So guys, if we could look inside of a crystal of sugar or a cube of sugar, it looks a little different. It's still crystalline, so it still exists in a lattice, but that lattice actually looks like this. Instead of alternating positive and negative things, sorry, I don't want to dig the waters out, but inside of a crystal of sugar, every single one of these points is a sugar molecule. You've got C6H12O6, or they do 11, C12H22. Each one of these is a sugar molecule. So when this thing dissolves in water, guys, what it's going to do is it's going to break apart, but the sugar molecules stay intact. So the water pulls this apart molecule by molecule by molecule. You'll notice that as these molecules go into solution, the covalent bonds inside the molecules don't break, so consequently we don't have any ions formed, and because we don't have any ions formed, there's nothing charged in solution, and if we hook a conductivity meter up to it again, it doesn't conduct electricity, and it's really slow. The light bulb doesn't light.
Cut.
You get the idea? Go ahead, Justin.
So are all ionic compounds electrolytes?
That's a really good question. And the answer for now is yes, but it's not really the answer. So let me back up on that. Let's take what you said one step at a time. Are all ionic compounds electrolytes? And the answer is actually, if they dissolve, yes. Because remember our solubility rules, right? We have some salts that don't dissolve at all, and we call those non-soluble. So the bigger answer to the first part of your question is, if a salt dissolves in water, it is an electrolyte. okay? Or it doesn't dissolve at all. With the molecular stuff, it gets a little more weird than that. But for now, we're just going to say if a molecular substance dissolves in water, it will be a non-electrolyte. You're going to see that exceptions to that rule are actually the strong acids. Strong acids actually contain covalent bonds, but when they break into ions. It's a little weird, but we'll talk more about it later. But for now, the answer is yes. Is that okay? Yeah, go ahead, Mark. That's a beautiful question, and the answer is they don't have a choice. Because if you think about it, the water molecules come in and they rip the ions apart, right? Talking about salts. And if you take the water out of the way, then those charged things reconnect with each other and form back into the salt. The thing that's interesting, have you ever done this, taken like salt water and boiled it dry? And the salt that's left doesn't look like anything that's in your salt shaker, right? Because you can actually change the way solids crystallized depending upon, many times, rate. That the salt that we have in our salt shaker formed over eons, and it's a very pretty regular crystal, which gives it its organized, it looks organized, right? But if you were to boil salt water dry, the stuff that's on the bottom is all flaky and crazy, right? The reason is because it forms so fast that it didn't have the chance to form that pretty organization that it would have if it had the time. Another place you see that is chocolate. Have you ever had a chocolate bar melt and then put it in the fridge and cool it back off again, and you pull it back out and it looks white? You know what I'm talking? That's why. Because what you've done is you've melted that chocolate bar, and when you put it back in the fridge and cool it cools off so fast it doesn't have a chance to form the regular repeated pattern that makes it look like chocolate, and it crashes into a solid and it doesn't look right because it's not forming the same crystal structure. Yeah. So guys, you good on these ideas? Okay, so now let's back up to Justin's question. So guys, Justin asked this, and it's a great jump off for us. So Justin said, I'm going to turn the lights back on. Justin said, are all salts electrolytes? And what did we say? Yes, if it dissolves. But now we need to dig in a little bit quicker or deeper into the answer, because it turns out, guys, not all electrolytes are the same. Some things are really good electrolytes, and other things don't break apart as well. And this is the next thing we need to talk about, because what we're talking about are types of electrolytes. And it turns out there are what are called strong electrolytes and weak electrolytes. And guys, would you do this for me, please? I'll actually do it with you. Where it says strong, would you please write the word complete underneath it? Guys, when you hear the word strong, you think strong. That's not what it means to a chemist. To a chemist, strong means complete. So what does that mean? What that means is if we've got a strong electrolyte, guys, think about this with me. What do electrolytes do? They dissolve in water, but what else do they do? Break into ions. A strong electrolyte does that completely. Okay? Keep that in mind. In the mind of a chemist, strong means complete. So, a strong electrolyte completely ionizes in water. Because it completely ionizes, these things are good conductors of electricity. Now, if we've got strong electrolytes, not surprisingly, we also have weak electrolytes. So guys, if strong means complete, what does weak mean? Incomplete. So guys, these things only partially ionize in water. I'll give you examples in a minute. And I'll show you a video in just a second. But guys, let's talk about an example. Let's talk about, I don't want to confuse, let's do this. Let's talk about HF. Guys, HF is hydrofluoric acid. Is hydrofluoric acid a strong acid? How do you know? Because you know the 7 that are. HCl, HI, HBr, HNO3, H2SO4, HClO3, and HCl4, right? That's why you memorize them. Those are the only 7 strong acids. If this isn't one of the 7, it ain't strong. And guys, strong in this context means the same thing as this. Strong acids completely break apart into ions. This is not strong. But when it breaks into ions, this is what it does. It breaks into hydrogens and it breaks into fluorides. But guys, this is not a strong acid, so it doesn't break apart completely. So what happens? It reaches equilibrium. As the HF breaks apart, some of the H's and some of the F's get back together and turn back into HF. So if you have a solution of hydrofluoric acid, you actually have some of this, and some of that because it reaches equilibrium. Now guys, what if you've got an acid like hydrochloric acid? Is hydrochloric acid one of the big 7? It is. So guys, hydrochloric acid breaks apart into H's and chlorides, but it doesn't go backwards. So that would make this a strong electrolyte because it completely breaks apart, and that would make hydrofluoric acid a weak electrolyte because it goes backwards and it reaches equilibrium, which means not all of these break apart, which means the solution that it forms doesn't conduct electricity as well. You get the idea? Is that okay? Yeah. Let's do this, and we're about to do this, but let's talk. So here's where we are. We've got we've got non-electrolytes and electrolytes, okay? Non-electrolytes do dissolve, but they don't break into ions. You okay with that? Okay, now we've got electrolytes. Electrolytes do dissolve, but they break into ions. And now what we're learning is that can happen one of 2 ways. Some of these electrolytes break apart completely. Those are called the strong electrolytes. Other of these electrolytes only break apart partially. And what they do is they reach equilibrium, and we call them weak electrolytes. Does that make sense? Okay, now what we're going to do is we're going to talk about what substances are strong electrolytes and what substances are weak electrolytes. But to your question, the strong acids are strong electrolytes, and there's only 7, and all the rest of the acids are weak electrolytes. But those aren't the only examples. So try it, but I may ask to wait. Go ahead, Mark. Now, why don't they do that? And I would propose to you, you don't get why hydrofluoric goes backwards. You know that it does, but the reason that it does is actually really interesting. And we're going to talk about it in March. For now, you just need to know that it does. It actually has to do with the hydrophilic nature of fluoride and chloride, but we're going to get to that later. Hydro meaning hydrogen, philic meaning loving, and we're going to get there later. Go ahead.
So what prevents the strong acids from reaching equilibrium?
And that's exactly, and we're going to talk about it in March. For now, you just need to know that's the case. Yeah, it's a fascinating answer, but it actually takes about 30 minutes to explain. Okay, so guys, here's where we're going now. We're going to flesh this out, and we're going to talk about what substances are strong electrolytes and what substances are weak electrolytes, but you may want to at least write down the word equilibrium. Because, guys, the strong electrolytes break apart completely. The weak electrolytes reach equilibrium. And Justin and Mark and probably more of you are like, why? Why do those break apart while those don't? Guys, I promise you we're going to get there, but for right now, it's going to be a topic unto itself a little later down the road. So now let's flesh out the list. Strong electrolytes. So guys, what substances are strong electrolytes? And the answer there are three. One of them are all the soluble ionic substances. But guys, what's the other term we use for ionic substances? Salts. So these are the soluble salts. But just to be clear, because I don't know if you've ever thought of it that way, this also includes the strong bases, right? We did those for the quiz. Sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. These guys. Those are technically salts. Guys, all of the strong bases are actually hydroxide salts. The thing that makes them strong is that they dissociate completely in water. We'll talk more about this next week. But guys, for our purposes, the strong electrolytes are the soluble salts and the strong bases. Both of those are ionic substances. And then also strong acids. So, the strong electrolytes are soluble salts, strong acids, strong bases. So what about the weak electrolytes? Well, guys, the weak electrolytes are the weak acids. There are thousands of them. If there are thousands of them, how do you know which ones are the weak acids? Because they're not the strong acids. It's that easy. If it's not one of the 7, it's weak. In addition to that, the weak bases are weak electrolytes. We'll talk more about this later, but the one that you should be aware of right now is NH3. We're going to be talking about NH3 a lot this year. You guys know what NH3 is? Ammonia. Not ammonium. Ammonium is NH4+. This is ammonia. And then, guys, the other thing that is a weak electrolyte are the slightly or partly soluble salts. There are some salts that don't completely dissolve in water. They partly dissolve in water. And we'll talk about, and you guys may remember these. I protected you from them last year. But if you remember the solubility table, S is soluble, I is insoluble. There's a P for slightly soluble. That's those. So there are some salts that don't dissolve completely. So if they don't dissolve completely, what do? Reach equilibrium. And was that your thought? Yeah. So if they don't dissolve completely, they reach equilibrium, and they reach equilibrium with their parts. I think you understand. You okay? Yeah. What? Yes, good. All of the weak electrolytes reach equilibrium. Yep, that's exactly the point. Yep. You guys good? Okay. So let me show you what this might look like.
Hydrogen chloride is a colorless gas.
So guys, this is hydrogen chloride. This is hydrochloric acid. This is interesting. Hydrochloric acid is a strong acid, right? How many strong acids are there? 7. Guess what? All of the strong acids are gases until you dissolve them in water, and then they become acidic. So all of the strong acids in their undissolved in water form are actually gases. And so this is actually a tank, just a second, Mark. This is actually a tank of hydrochloric acid. There's no water in here. It's just the hydrochloric acid gas. So we don't call it hydrochloric acid. An acid until it goes into water. So,
which is soluble in water and benzene. First, pure water is poured into a beaker.
So guys, I know this is sort of hard to see. Let me see if I can zoom in a little. So here's what you've got. You've got a light bulb, kind of like the thing that they jammed into the animations I showed you before. You've got a beaker right here that he's going to put water in, and then we're going to open up the valve on the hydrogen chloride gas and bubble it through the water. Now, as it bubbles, it will dissolve. What you might be able to see is that there are electrodes stuck down into the beaker. So there's going to be water in there. The electrodes will be in the water. Now, first of all, when we pour the water in there, will the bulb light up? Why not? Water doesn't conduct electricity, right? So the water won't conduct electricity because there's no charged particles in water. It's H2O. And so that won't conduct electricity. But guys, when we bubble the HCl through the water, is HCl a strong electrolyte? Yeah. So what will it do? It will break into ions, and what's the light bulb going to do? There you go. So here we go. So in goes the water.
Water has a very low conductivity, and the bulb remains unlit. When hydrogen chloride gas...
Do you see it? Now we're bubbling the hydrogen chloride gas through. It's ionizing. Those hydrogen and chloride ions conduct electricity, and the light bulb's going crazy.
passes into the water, it dissolves, and the bulb shines very brightly, showing that the solution is conducting. Ions form because water behaves as a base, accepting protons from the hydrogen chloride. We get the hydronium ion and the chloride ion. In the last part of the experiment...
Okay, so now we're going to do this again, only now we're going to use a weak acid, which is acetic acid, which is vinegar. So same deal, pour in the water, what's going to happen to the light bulb? Actually, they don't. They just pour the acetic acid is already dissolved in the water. So guys, when they pour the acetic acid into the chamber, acetic acid is a weak acid. So it's a weak electrolyte. So does it break apart into ions? A little bit, right? So it will break into ions, but what do those ions do? Go back. And so at any given moment, some are breaking apart, some are going back. So will we have some ions? Yeah, just not very many. So what's the light bulb going to do? It's going to glow dimly. Yep, here we go.
We are using a weak acid, acetic acid. We pour 0.1 molar acetic acid into the beaker. And the light bulb glows less brightly, showing that the solution has only a small conductivity. Acetic acid is a weak acid and is only slightly ionized in water.
You get the idea? All right. So, go ahead. Yeah. You ready for this? You're going to feel ripped off. So you understand that Gatorade is an electrolyte sports drink, right? But what do you now know electrolyte means? Salt water. It's not a strong acid, right? Because that would be bad. So it's also not a strong base, so that would be bad. So the only thing that's left is salt. And so when you drink Gatorade, you're literally drinking salt water. Yeah, that's the trick. The genius of it, and you know where Gatorade came from, right? The Florida Gators. It was actually developed at the University of Florida, and so they called it Gatorade because they gave it to the Florida Gator football player. Anyway, so what they were finding is that, you know, especially in Florida where it's so hot and humid, as they get deeper into the fourth quarter, their athletes were cramping up and they couldn't figure out why. And they started doing blood draws on these athletes, and what they found out was that the sodium and potassium levels in their blood were really depleted. And the problem is they were sweating it all out. Well, the problem, if you've taken biology, is that nerve impulses, which are literally just electrical currents. Our body has this amazingly complicated like system of wires that move all throughout our body that are our nerves. And the way that our body propagates these electrical signals is by pushing ions, specifically sodium and potassium, in and out of the cells. And if we run out of sodium and potassium, our nerves can't transmit these signals anymore, and our muscles go, crap, I'm confused, and they contract and you cramp. And so these guys at the University of Florida said, we need to start getting salts back into our athletes. And they basically took water, put sodium and potassium salts in there, added red stuff that tastes good, and fed it to their athletes, and it worked. So that's all it is. And now they put sugar in it because you need the calories to sustain activity. But that's all an electrolyte drink is just salt water. And it replaces the electrolytes that you lose.
So is it bad to drink Gatorade if you're not losing all the salts?
Yeah. Oh, absolutely. Yeah. So, and like if you're hypertensive, like if you have like high blood pressure, the first thing they're going to tell you if you're an athlete is stop drinking Gatorade. Because even as an athlete, if your blood pressure is high, sodium just further elevates your blood pressure. And so, yeah, they'll pull you off of that stuff. Yeah, no question. But like I cycle with people that will actually, they can't drink Gatorade because they don't like the taste. They'll actually eat salt tablets. I can't get myself, do you know people that do that? I can't do it. But yeah, I ride with people that just down salt tablets because it's an easier way to replenish those electrolytes. What's that? Yeah, you can. You can just, the problem is that there's limits to how much of that salt you can absorb out of your gut in any given time, and most of it just passes through anyway. So it doesn't always help. So, guys, we are now done with this conversation about strong and weak electrolytes. What questions do you have as we move forward? You guys okay? Okay. So let me pause for a second. Okay. So, guys, you know that in general chemistry, things get chunked into days and we push through and have you ever noticed how in general chemistry, within like 5 minutes, class always seemed to end right when the bell was going to ring? Yeah, we're good that way. But guys, one of the things that's interesting about AP chemistry is that days are different. And I love it because it allows us to reflexively move through material. But sometimes what that means is we may have to say, we're not going to get done with all of the material that I necessarily thought that we would. And how do you know what I thought we'd get through? That's the notes. Those are the slides. And so if you printed the slides, you're going to see we've got a fair bit more material to cover. And to be honest with you, we could crush through this in the next 13 minutes. But the thing that you're going to learn to do next, you have to know how to do for the rest of the year. Actually, I'm going to teach you a brand new way to write balanced equations. These things are what are called net ionic equations, and this is critical because every single balanced equation that you will write in this class for the rest of the year will be a net ionic equation. And if I were to crush through that, it would be a huge mistake. So guys, what we're going to do is we're actually going to stop here. That doesn't mean you're done, but it does mean we're going to stop here. But that creates a problem. So, and Jeanette, if you could communicate this to Susanna, because I think she's going to go home and try to crush through all of this. Chat with her and let her know. So guys, here then is the deal. This is your homework. Go ahead and write this down with me. So guys, your homework is 2, 3, 5. And guys, you'll notice when it says 5, they forgot to give you the charge of the lead ion in question number 5. Assume it's +2. Then number 12. And when you do, this is not in the instructions, but I'm going to ask that you do this. Draw the two solutions that you're talking about. then 15, 18, 20 through 24, and 27. Oh no, I'm sorry, skip 22. 20, 21, 23, 24, 27. Did you get it? You okay? Now do this with me. What? Skip 22. But now, guys, watch this. With that list in front of you, go to the end of chapter 4 with me. So turn to page 150. Starting at the top of page 150, guys, you'll notice that as in chapter 3, the first questions are the visualizing concepts. But then, guys, after that, you'll notice the headings lead you section 4.1, section 4.2. Now, guys, section 4.1, general properties of aqueous solutions. That's what we just did. Strong and weak electrolytes, non-electrolytes, that kind of stuff. Now, guys, going to the top of page 151, notice what it says. Precipitation reactions. Have we talked about that yet? No. Because we haven't talked about that yet, you can't answer those homework questions. So, guys, where does that section start? Question 19. See what I'm saying? So anything past question 19, you can't do because we haven't got there yet. So guys, basically your homework for tonight is just through question 18, and then 20 through 27 will be your homework after Tuesday because we're going to split this particular day into two. Do you see what I'm saying? So guys, typically what we'll do is when we get together on Tuesday, I will ask you. Now, sometimes I'll just tell you, but sometimes I'll ask you, do you want to grade homework or should we just get started and grade it as one assignment on Thursday? So we'll talk. But guys, bottom line is you still have 9 minutes. So I want you to start on the homework. It's up on the screen, but we are going to stop there. We'll do questions and then we'll work on homework for the next 10 minutes and then we'll pick up where we left off on Tuesday. I will be collecting that. Guys, let's say it again. What's true of these chapter outlines? They're grade padding, right? Don't turn them in late. You can, but don't because you'll lose points. Guys, this is me helping your grade to not be horrible. So guys, take advantage. Yeah?
So, isn't it, we just write it in the book?
What?
The chapter outline?
No, on paper. Did you just mark up the book? Yeah, no. So the idea is you're putting that outline on paper.
Okay, so we'll just go through and like...
Roman numeral 1, yeah.
And we'll write, so for instance, it'll say like...
Okay, so let's start on page, starting on page 116. Roman numeral 1, general properties of aqueous solutions. Oh yeah, capital A, electrolytic properties, right? Then number 1, whatever you found interesting. Number 2, whatever you found interesting. Then over on page 117, capital B, ionic compounds in water, and then flesh that out.
Okay, so just
Yep.
however much you think we need
Yeah.
for the 1, 2, 3.
You got it. Yep. Somebody else had a question.
Oh, I was gonna say, so we just mark summary of the graph.
Yeah, so, the summary of the solubility table, so I'm never going to collect that from you, but we are going to reference it when we do precipitation on Tuesday. Okay. Just a second. Go ahead, David.
When we do these, it's just how we feel like we should.
Exactly. Yeah, go ahead, Mark.
So are you expecting for the solubility, like guidelines?
Yeah, so guys, let's talk about this. Ready? I don't know how to say this, so let's just say this. Guys, you understand your goal in this class is not to get 100% on the AP test, right? You're not shooting for a perfect score on the AP test. right? There are going to be things on the AP test you're going to skip. There are going to be things on the AP test you're going to get wrong. Your goal is to do well enough, but not try to learn everything, because trying to learn everything would drive you into an insane asylum. To your question, what is this summary of the solubility table supposed to look like? The answer to that is different depending on who you are. I don't have a photographic memory. So if you look at that table on whatever page it is, if you have a photographic memory, maybe your summary is all the little details. But I'm not a detail guy. I'm a big picture guy. I'm a relational guy. And so I have said, I want to know the big ideas. So my summary of that table goes like this. All the nitrates dissolve in water, all the sulfates dissolve in water, all the halogens dissolve in water, all the acetates dissolve in water, all of the group 1 and heavy group 2 salts dissolve in water, and exceptions for that tend to be around silver, lead, and mercury. That's good enough for me. Now I've got enough of the solubility rules that 90% of the stuff you throw at me, I can figure out if it dissolves in water. But even some of what I just said to you isn't actually true. So there are some other gaps that I'm just willing to let go of and get wrong, or look up in a book. Understanding you won't have that book during the test. So you need to decide. So Mark, if you're like, no, I'm the kind of person that needs to know all the little details, then maybe your summary is more detailed. But for me, I'm like, hey, that's good enough for me. And that's going to have to do. And it gets me 90% of the way there, and that's going to have to be close enough. You know what I'm saying? So, guys, the rest of the time is yours. Now we're like 4 minutes. I forgot to stop recording.